All right, so we have a particle that's at rest. So the starting momentum is 0. I'm just going to go ahead and write the conservation of momentum here. Total momentum before the explosion equals the total momentum after the explosion. And we actually have 0 momentum before the explosion. Everything is at rest. There's 3 particles that come out of this explosion. So I'm going to say momentum of E for the electron after the collision, plus momentum of N, the neutrino. Yeah, I'll use N. And then the momentum of the third particle, I'll just say 3. Okay, so that's the conservation of momentum right there. And we're actually given 2 of the momentums out of the 3. We have to find the third velocity. And you're going to draw a little bit of a diagram first, though. So it starts at rest here. So this is before. Kind of a boring picture before. Now we'll do the picture after. So what's going on after is we have 3 pieces shooting out of this. So one piece, the electron, is going east. And the velocity is not given, but the momentum is. The nehru's are given, or kilogram meters per second are given. And that's east. And then the neutrino is another particle, and it gets blasted south. And its velocity is not given, but its momentum is. It's given as 5.40 times 10 to the negative 23 nehru's south. So can we kind of predict which direction the third particle is going to be blasted? Well, see, the momentum has to be conserved. So since the starting momentum was 0, this means when I add up all 3 of these momentums, it needs to balance out to 0. So I think that's going to end up being in some kind of a northwesterly direction. Not 45 degrees, because those 2 components are not equal. So that's going to be, I'm going to label this as P3, momentum of particle 3. And that's what we have to find out. You got to find out both the magnitude and the velocity there. So one way to do it is to analyze individual components, x and y. And the way I see it, it might not actually be too complicated. Let me draw the components in for this third one. So I'll call this P3x and P3y prime. So for everything that makes 0, I think simply the x component needs to be 9.3 times 10 to the negative 23. It needs to match the electron's momentum, and then the y component needs to match the neutrino's momentum. Then I can use the Pythagorean theorem, because this will be a right angle triangle. I can use a Pythagorean theorem to figure out the hypotenuse. I can use inverse tangent to figure out the angle, which is one approach. Or the second approach, which I'm going to do, is to actually just use vector addition or vector subtraction and use a calculator there. So if I look at my algebra, the conservation of momentum algebra here, what if I rearrange this for P3? If I rearrange it for P3, it's basically just going to be negative the electron's momentum and then minus the neutrino's momentum. That's what it'll be. So it will be, I'm going to rewrite this with numbers and directions. So it would be negative east. I'll do it in 2 steps. It'd be negative 9.3 times 10 to the negative 23 Nehru's east and then minus 5.40 times 10 to the negative 23 Nehru's south. But I'm going to change these negatives to positives and flip the directions. So this would become positive 9.3 times 10 to the negative 23 Nehru's west plus 5.4 times 10 to the negative 23 Nehru's south. So this, I'm going to put a green box around it. This is what I have to calculate to get my answer. It's vector addition because west and south they're not parallel to each other. So I have to do it by drawing a triangle. But I'm actually going to throw that into the online vector addition calculator. And when I type it in, how do you type scientific notation into the calculator? I would actually type in 9.3e negative 23. So that e in this calculator represents times 10 to the exponent of. For west, so this calculator makes east as 0, and it goes counterclockwise. So west would be the opposite direction, so that would be 180 degrees. I will type into this calculator. And then I would type in 5.40 e negative 23. And south, no, that's wrong. It should be north. I didn't change it for some reason. Negative south is north. So north, east is 0 degrees and go counterclockwise. So when I get to north, that's 90 degrees. So this is what I'm typing in to my vector addition calculator. And I did that on the next slide. And this is the answer they gave me. Okay, so that represents the momentum of particle 3 after the collision. It would be 1.0754, that would be to 2 sig figs, times 10 to the negative 22. And the angle would be 150 degrees. So if east is 0 degrees, where's 150? So you have 90, and then 60 more degrees would give me 150 degrees. So it would be 60 degrees here. So the direction of this thing is north 60 degrees west. And this is in Nehru's. The question asks us to find the velocity. They tell us the mass of this particle. It's on the previous slide. They told us the mass was 1.67 times 10 to the negative 25 kilograms. And we can actually solve for the speed now, or the velocity. because momentum equals mass times velocity. So velocity will be momentum divided by the mass. So I'll just divide those two numbers. Okay, so 1.0754 divided by 1.67, and the powers of 10 as well. Okay, so I'm ending up with 644. Okay, so that would be the velocity of the third particle.